Okay guys, so welcome back. So I hope you already watched my previous video which already explained to you about reversible reaction. Okay, so I already explained about dynamic equilibrium and on how to write the expression for equilibrium constant in both in the terms of concentration and partial pressure. Okay, so for our today's video, we're going to learn on how to calculate or solving problems involving equilibrium constant, either in the terms of concentration or partial pressure. Okay, so by the end of this lesson, you're going to be able to solve two types of equilibrium constant problem, which is first either to calculate what is the value for your equilibrium constant, or secondly, okay, by the use of special table known as ICE table, okay, to solve any other quantities that you need to calculate throughout the problem. Okay, so I promise to you this one going to be a very long video, therefore I give you ample of time now. Go and grab a popcorn, okay, to help you keep focus in my video. Then take calculator, grab a few pieces of A4 paper, pen, as well as grab your mind as well, so you're going to stay focused till the end of this video. Alright, because in this video I already prepared a few quizzes that you need to submit to me before our next class. Let's discuss on the problem type 1, which is to calculate equilibrium constant. So this one is just a simple problem which you can just simply substitute the given quantities into solving your Kc or Kp values. Okay, so let's look at question 1. So you have to calculate what is the equilibrium constant for the following reaction at 350 Kelvin. Okay, so they give you the initial moles for nitrogen, oxygen, and NO2. Okay, so to calculate Kc, that means you need to calculate what is the concentrations of all of these gases. Okay, so to calculate concentration from the given mole is just simply mole divided by volume. Okay, so let's calculate concentration. Okay, so concentration, so N2 is 2.50 mole divided by 2 dm cube. For my oxygen is 3.50 mole divided by 2 dm cube. And for my NO2, 0.06 mole divided by 2 dm cube. Okay, so this one is equivalent to 1.25 molar, 1.75 molar, and 0.03 molar. So let's write down the Kc expression first. Okay, so Kc, we're going to use square bracket to represent the concentration. Okay, so product cos NO2, okay, concentration, n to the power of 2, because stoichiometric coefficient of NO2 in the equation is 2, so make it as a power. Okay, and then concentration of N2 time with the concentration of O2 to the power of 2 again. After writing down the Kc expression, then now you can substitute it with the value. Okay, so 0.03 to the power of 2, okay, over 1.25 time with 1.75 to the power of 2. So if you press your calculator, you will get your Kc to be 2.351 times 10 minus 4. Okay, as you listen in your my first video, I already mentioned to you that in our syllabus the Kc has no unit, so you can just simply write down the value and leave it out as that. Okay, so to score a good mark for this one, first mark is given when you calculate the equilibrium concentration for each one of the gases component correctly. Second mark is given when you write down the Kc expression correctly. And for the substitution process as well as in the final marks. So this one can cost you about 4 to 5 marks. Okay, it's just simple. Okay, let's look for exercise 2. Okay, so you are given a process of water liquid to change into a gaseous water, and you are asked to calculate Kp for the reaction given that the vapor pressure of water at 25 degrees Celsius is equivalent to 23.8 torr. Okay, so this one, so Kp equals to partial pressure of H2O, and it's a round bracket. Okay, so when you're writing down your Kc and Kp, all pure solid and liquid will be removed from the expression. Why? Because we assume that their concentration remain constant till the end of time. Okay, so remains constant, so that's why we don't include the value into the calculation. We don't include any solid or liquid component in the Kc or Kp expression. Okay, so we just have Kp to be partial pressure of water, and given that partial pressure of water is 23.8 torr, so 23.8, that's it. Okay, so let's go on for a more difficult question, which is type 2, where you're going to meet ice table. So ice table is a special table which consisting of I stand for initial, so either initial concentration or initial pressure. C is for changes, either changes in the terms of concentration or pressure, and E here is referring to equilibrium. Okay, equilibrium, concentration or pressure. So we're going to use a lot in this ice table to solve a more complicated problems in your chapter 6. Okay, so ice table will also be applicable in your chapter 7 later on. So you need to really understand what is ice table and how to use it. Alright, so let's try with a more difficult question which involving ice table. So what is ice table? So ice table involves initial for I, changes for C, and equilibrium for E. Okay, so some questions might ask you to calculate Kc. So initial referring to initial concentration, changes in concentration, and equilibrium in concentration. So when it is involving concentrations, okay, you can simplify your writing with initial and a square bracket, and please don't forget to write down what is the unit involved. Okay, so concentration is in molar, changes concentration in molarity as well, and equilibrium concentration is also in molar. Okay, so you were given a reaction between hydrogen and iodine to form hydrogen iodide. Okay, first thing first, always check either your chemical equation is balanced or not. If it's still not balanced, then you have to balance it first before you begin with filling up the ice table. Okay, because if let's say you still having an unbalanced chemical equation, so whatever the answers that you get throughout the calculation later on will be entirely wrong. Okay, so let's check. We have 2 atoms of hydrogen in the reactant and 2 atoms of hydrogen in the product. So 2 atoms of iodine in the reactant, so we have 2 atoms of iodine as well in the product. So your chemical equation given is already balanced. Okay, so sometimes the reaction might be proceeding in a forward direction. Forward means from left to right, so this is forward again. Okay, but sometimes the reaction is proceeding in a reverse direction. Okay, reverse means from right to left, so you have to be alert because the changes involved here, okay, will depends on is it a forward direction or a reverse direction. For changes, we will use X to represent changes. Okay, so X to represent changes. Okay, and we have the magnitude. Either it's positive or it's negative. Okay, depending on which of the compound is being produced. So if it's being produced, it will be positive X. If it being used up, it will be negative X. Okay, so the X value can be 1X, 2X, 3X. Entirely depends on the stoichiometric coefficient in front of the compound in the chemical equation. Okay, so for example, in this example, you were starting your reaction with hydrogen and iodine, okay, with 0.20 mole. Okay, so to get concentration, just simply number of mole divided by volume. So 0.20 mole divided by 2 liters, you will get 0.10 molar. Okay, same goes on with your iodine. The same number of mole with the same volume, so it's 0.10 molar. Okay, so we start with hydrogen and iodine, and there is no information about the initial concentration of hydrogen iodide, so we assume it is just 0. Okay, changes is in the terms of X, and hydrogen is being used up, so negative, and it is 1 here, so negative X, and 1 here again in iodine, so negative X. Okay, whereas in the reaction, we are producing hydrogen iodide, so the reaction goes in a forward direction. Okay, so there are 2 moles of hydrogen iodide, so positive here indicates producing, 2 because of the stoichiometric coefficient in front of the hydrogen iodide, and X referring to changes. Okay, so equilibrium concentration is initial minus changes or initial plus changes. Okay, so actually initial plus changes. So this one 0.10 minus X, this one 0.10 minus X, and this one is positive 2X. Okay, so equilibrium concentration equals to initial, okay, plus changes. Alright, okay, so the question gives you, at equilibrium the concentration of iodine had dropped to 0.020 molar. Means drop to means the final concentration is 0.020 molar. Okay, so what is the value of Kc for this reaction at this temperature? Okay, so first you need to calculate what is the value of X. Okay, so 0.10 minus X equals to 0.020 molar. So your X is actually 0.10 minus 0.020, and your X is equivalent to, how much is it? It is 0.08 molar. Okay, so you have to calculate equilibrium concentration. Okay, for first, my H2, which is 0.10 minus X equals to 0.10 minus 0.08, and you will get 0.02 molar. Okay, for your iodine, it's the same, 0.02 molar. And thirdly, for my hydrogen iodide, so the concentration at equilibrium for hydrogen iodide is equivalent to positive 2X. So your X is 0.08 molar. And when you press your calculator, you will get the answer to be 0.16 molar. Okay, so now you have to calculate Kc. So first, writing down the Kc expression. So square bracket Hi square. So product over reactants. Okay, so which one is being produced, it will be on the top, and which one being used up is in the bottom. Okay, in the numerator side. Okay, I2. Okay, then you substitute with the form, the value equilibrium concentration. Okay, so for hydrogen iodide is 0.16 power of 2. Where did you get this 2? The 2 comes from the stoichiometric coefficient in front of the Hi, which is 2. Okay, so for hydrogen, it's 0.02 time with the iodine as well, 0.02. So your answer for your KC is 400. And strictly no unit. It actually has unit, but for your current metric syllabus, you need to just ignore the unit of your KC and KP. Okay? And so let's try with a different question. Okay, question 4. Okay, in the reaction, okay, you are given this chemical equilibrium. Okay, from NO2. Okay, 2 moles of NO2 is producing N2O4. So 2 atoms of N on the left side and 2 atoms of N on the right side. So N is balanced. And for oxygen, 4 atoms on the left and 4 oxygen atoms on the right. So definitely a balanced equation. So the reaction begins with 0.100 molar of N2O4. So we begin with N2O4. Okay, again, unit here. So that means instead of proceeding in the forward direction, this reaction takes place in a reverse direction. Okay, so now your NO2 is your product instead of reactants. Your NO2 is the product and N2O4 is our reactant. Okay. Okay, so that means our NO2 initial concentration is 0 because they give you no information at all about NO2 concentration, so assume that's 0. At equilibrium, the concentration of N2O4 was measured as 0.009 molar. Okay, first let's fill up the ice table. Okay, so N2O4, okay, you are supposed to have 2 NO2 here. Okay, since NO2 is being produced, so it's positive, produced, okay, positive. And we have 2 moles of NO2 on the reactant side, so 2 and changes is X. Okay, N2O4 is being used up as the reactant. Alright, so it's negative and it's 1 mole of N2O4 present, so negative X. So at equilibrium, okay, NO2 is positive 2X. Okay, just simply add up both initial and changes. And for the N2O4 is 0.100 minus X. Okay, so they give you what is the equilibrium concentration for N2O4, which is 0.009. That means you can calculate what is your X value. Okay, so 0.100 minus X equal to 0.009. Alright, so your X is actually 0.10 minus 0.009, which is equals to 0.091 molar. Okay, so your NO2 is positive X, so equilibrium. Okay, first NO2 equals to 2 times with 0.091. Okay, so you will get 0.182. And for your N2O4 is simply 0.009. Okay, it's better for you to calculate and choose your equilibrium concentration one by one, so that and calculate for all of the reactants and products that is present, so that you'll not get any mistakes in the calculation later. Okay, so your KC, okay, writing down the expression first. Since our product is NO2, so it will at the top NO2 and to the power of 2. Because stoichiometric coefficient for your NO2 here is 2. Okay, over N2O4. Okay, then we substitute with the equilibrium concentration that we already calculated here. Okay, so your NO2 is 0.182. Okay, square over 0.009. Okay, so if you press your calculator, you will get your KC to be 3.68. Again, no unit. Okay, and so we have made 2 types of questions which involve calculating KC value. Okay, so if let's say you have to calculate KP, it's still initial here, but instead of concentration, we will write down pressure initial and the unit is ATM. Pressure changes and the unit is ATM again. pressure final is ATM. So it depends on what is the unit given to you. If it's ATM, then it's ATM. If it's store, it's store. You don't have to convert it to any other units. Okay. Alright. So let's try now. When you were given a KC, you need to find out the changes. What is the equilibrium concentration? So this one you require to have a quadratic expression mode or function to calculate x in your calculator. If you use an old school calculator, you will not have this function, but that's okay. You still can download the scientific calculator apps in your Play Store or in your App Store, so it's available. Okay, so don't worry, you still have the chance to purchase your calculator at the bookstore. Okay, please make sure you get one before your PSPM, okay, because it really helps, because this one is not a simple quadratic expression like you used to have in the high school where factorization can be helpful, but this one involves a very complicated quadratic expression, so a calculator is needed with that function to calculate what is the x value. Okay, so x will always make our life difficult. That's why please don't have any x in your life. Okay, so question 5 here. Okay, so we are given bromine reacting with the chlorine to form a compound of mixture of both. Okay, so now they give you Kc with 720. Okay, for every questions involving Kc, they will give you the value with the setting of the temperature, because later on in your next video about Le Chatelier's principle, you will learn that your Kc or Kp value varies depending on the temperature. Only temperature can change the value of your equilibrium constant, or else your equilibrium constant value will be fixed, provided it is at a constant temperature. Okay, I will elaborate in detail more about these changes in your Le Chatelier's principle video. Okay, so for now, let's focus on calculation only. Okay, if the reaction vessel contains these two gases with initial concentration of 0.20 molar. So the two gases is mentioned here is bromine and chlorine. So let's fill up your ice table, okay, with the given information. So we have 0.20 molar of bromine, 0.20 molar of chlorine. So that means 0 molar for your bromochloride. Okay, calculate the equilibrium concentration of BrCl. Okay, so first let's do the changes. So we are using up bromine and chlorine, so minus x. Why x? Because it's only 1 mole of bromine here and 1 mole of chlorine. So minus x, and for our product we have 2 moles and plus 2x. Okay, so equilibrium is just simply initial plus changes. So 0.20 minus x, 0.20 minus x, and plus 2x. Okay, so we have to calculate x here first before you can calculate equilibrium concentration. So let's write down the Kc expression first, which is BrCl square. Square comes from the stoichiometric coefficient over Br2 and Cl2. Okay, then equals to 7.20. Okay, now I'm going to substitute the expression with the value given, okay, in the terms of x. Okay, so BrCl2 is 2x to the power of 2, and then this one 0.20 minus x and 0.20 minus x equals to 7.20. Okay, so you have to expand the one at the bottom first. Okay, so 4x squared, 2x squared is equivalent to 4x squared over, alright, so it is 0.04 minus 0.40x plus x squared equals to 7.20. Okay, so you're going to make it in just one line. So everything down here you will multiply with 7.20. So 4x squared equals to, okay, 720. Multiply with everything first. show your calculation so you won't get confused. Okay, so I expand it by multiplying everything with 7.20. On the right side, so I will get 0.288 minus 2.88x plus 7.20x squared. Okay, so I'm going to move my 4x squared to the right side so I can replace it with 0 to enable me to form a quadratic expression and solve it. Okay, so 720 minus 4, 3.20x squared. Okay, rewrite. Okay, so if we compare with our quadratic expression, so this is our A, negative 2.8 is our B, and 0.2288 is our C, so positive. So press your calculator, so you will get x1 to be 0.1146 molar. Okay, leave it up to 3 to 4 significant figures, and x2 to be 0.7854 molar. Okay, so the smallest x value will be accepted. So this one you write down accepted, and the other x value will be rejected. So you have to label your answer. Which one did you accept and which one you reject? Okay, so you were asked to calculate equilibrium concentration of BRCl, which is positive 2x. So BRCl equilibrium in molar equals to positive 2x equals to positive 2, 0.1146, and you will get your BRCl concentration at equilibrium is equivalent to 0.2292. Okay, this one is concentration, so it have your unit of molar. So never forget your unit. Okay, so how was it? Is it easy or is it difficult? How do you find it? It's quite hassle, okay, to solve your x value. All right, so never mind. Okay, let's give you another one example to calculate x again. Okay, so now hydrogen reacting with iodine to form hydrogen iodide, and you were introduced with 0.15 mole of hydrogen. So instead of giving the concentration, now they give you moles, but that's okay. You can calculate concentration from the given mole by simply number of mole divided by the volume. Okay, so 0.15 mole divided by 15 liters, so you will get 0.10 molar. Okay, so now let's do for your iodine. Okay, it's 0.10 molar. Sorry, if you press your calculator, you will get 0.01 molar. 0.01 molar. Okay, for iodine is 0.20 mole divided by 15 liters, so you will get it to be 0.013 molar, and hydrogen iodide is being produced, so 0. So changes: hydrogen negative x, iodine just 1 mole and is being used up, so negative, and it's x, and hydrogen iodide is positive 2x. Okay, so this equilibrium reversible arrow should be between hydrogen iodide here forming. Okay, so plus actually. Alright, okay, so equilibrium concentration 0.01 minus x, 0.013 minus x, and plus 2x. Okay, so what is the next step? Okay, the next step is you have to write down your Kc expression first. Okay, so Kc equals to Hi square over H2 and I2, which is equals to 50.2. Okay, now after writing down the expression, now you can substitute the concentration with the equilibrium concentration in the terms of x. So 2x square. Okay, so 0.01 minus x and 0.013 minus x. Okay, next step, what should you do? You have to expand. Okay, so 4x square, and at the bottom one, if you expand, you will get 1.3 times 10 minus 4. Okay, so minus 0.023x plus x square. Okay, so we're going to make it into just one line. So everything down here you will multiply with 50.2. Okay, so 4x squared equals to 50.2. And I'm going to multiply with everything. But first, write down here so you won't get confused. Okay, so then expand by multiplying everything with 50.2. Okay, so you will get 6.526 times 10 minus 3 minus 1.1546x plus 50.2x squared. So if you want to solve this quadratic expression, again, you need to leave out 1 to be 0. So just move 4x squared to the right. So 50.2x squared minus 4x squared, you will get 46.2x squared minus 1.1546x plus 6.526 times 10 minus 3. Okay, so this is your A. Negative 1.1546 is your B. Please make sure you include the negative sign. And this one is your C. Okay, so you will get, if you press your calculator, you will get two different x value. Okay, so your x1 is 0.00864 molar, and your B is, your second value is 0.0164 molar. So accepted is the smaller one and rejected is the second one, the bigger one. Okay, so then the question asks you how many moles of HI will present. So to calculate moles, you need to know the molarity of HI at equilibrium first. Okay, which is 2x equals to 2 times with 0.00864 molar, and you will get your equilibrium concentration to be 0.01728 molar. Okay, so molarity is, okay, so molarity equals to number of mole over volume. So to get moles, you just simply molarity times with volume in liter. Okay, so N equals to 0.01728 molar times with the volume of the flask, which is 15 liters. Okay, so you will get the number of mole to be 0.2592 mole. Okay, so that is the number of mole of number of mole of HI at equilibrium. So this is NHI equilibrium, which is 0.2592 mole. Okay, so I have shown to you two different calculation. Okay, for question 3 and 4. Okay, so we discuss on calculating Kc from the given initial concentration, whereas question 5 and question 6 we discuss on how to calculate x value, okay, and x value, and then calculating equilibrium concentration or any other sorts of questions related to it from the given Kc or Kp value. Okay, so now I'm going to give you the final questions, which should be your quiz one. Okay, so these questions, please try to do it on yourself. Okay, even though I have not yet using the ice table. Okay, I didn't show to you using ice table with the terms of partial pressure, but like I said before, it's just the same ice table, but instead of in the terms of concentration, we are changing it into partial initial partial pressure, changes in partial pressure, and equilibrium partial pressure. So simply using the same ice table but now in the terms of partial pressure. Okay, so have given an attempt to answer these questions, and I will give you the final answers during our third hour tutorials. Please make sure you try to do it before our third hour tutorials, and I will ask you to submit through our Google Classroom for me to look at your calculation steps. Okay, so thank you for watching, and going to see you guys again in my next video. Bye bye.